Hi everyone. So this is live interactive session for week 5 of the course Structural Geology offered by NPTEL. And my name is Rajiv Mukherjee and I am currently hosting these live sessions for the 12-week duration of the course. And today's topic of discussion is problems on rheology. So talking about the course outline, we already have covered up to week 4. In the last week, we even discussed about the concepts of stress, and the week before that, we talked about the concept of strain and deformation. So, in week 5 for the course Structural Geology, we mainly learned about how stress and strain are associated for a rock. That means when a rock is deforming or any kind of material that is deforming, so how the material deforms in response to the applied external stress is the main idea of studying rheology. So this is week 5's content, and this is the live interactive session. Today's date is 24th August. This is the 5th live interactive session, and this live interactive session will be hosted for 12 weeks of duration. So we are on the week 5, another 7 weeks to go. And the live sessions are hosted on every Saturday of each week from 4 p.m. to 6 p.m. of duration. And this is the session link to join the live discussion session. Okay, so moving on to the discussion session today, I would briefly summarize that what we have learned in week 5. So in week 5, our main target was to know about the concepts of rheology, elastic, viscous and plastic deformation mechanisms, classification of deformation processes in terms of rheology and internal cohesion, applications of rheology in our daily life. Then we talked about elastic constants of a material like Young's modulus, Poisson's ratio, rigidity modulus, bulk modulus, etc. And then we also learned about the concept of the generalized Hooke's law and the concept of stress strain diagram of a deforming material. From that, we also knew about strain hardening, strain softening, and ideal plastic behavior of materials. And then you also knew about linear viscous materials, combination of different kinds of rheological models like the Kelvin-Voigt and Maxwell's model of viscoelasticity, constitutive equations of viscoplastic materials. And then we talked about the application of rheology in geodynamics, particularly in terms of plate tectonics, in the scale of plates, mantle convection, and how earthquake can be related to different kinds of rheological models. And in the final lecture of week 5, there was the effect of external parameters such as pressure, temperature, and pore pressure on the deformation responses of our materials. Okay, so from that perspective, in today's live discussion session, we will mainly be solving conceptual problems related to rheology, stress strain relation of different kind of rocks, and then we finally will see some problems that are readily related to geodynamics. And then I will summarize in conclusion for today's discussion session, and we will briefly have a live plan for the upcoming live session. So with any further ado, let us move on to the question answer sessions for this week's live discussion. Okay, so the first question tells us that which of the following physical properties of a monoclinic crystal will likely to change if the crystallographic orientation of the mineral is changed? And there are 4 options given. First is Young's modulus, then bulk modulus, then density modulus, and finally the compressibility. So the question is asking is that whenever we say we talk about changes in physical properties, changes in physical properties, based on directions, based on, or we can say with respect to directions, that essentially means that we are dealing with anisotropy of the material. So this means that we're talking about anisotropy. So isotropic property means that there will be no change of physical parameters based on directions. So homogeneous and isotropic, heterogeneous and anisotropic, they are not the same. As we already have known that homogeneous essentially talks about the distribution of particular physical parameters with respect to the volume. Right? So if I have a volume of rock and then I say that is the distribution of quartz inside this rock is homogeneous, then that will be an appropriate question to ask, because we know that the distribution of quartz essentially is its modal percentage will depend on the volume of the rock we are talking about. But anisotropy or isotropy is a property, not property, is how the physical properties or even chemical properties as well, they are related to the directions inside that material. That is isotropy or anisotropy. And anisotropy means that there is a change with respect to direction. Whenever you're talking about direction, if there is a direction, specific orientation, and perpendicular to some angle to that orientation. So if there is a change in the physical property that we're talking about, then that is anisotropy. So keeping in mind that concept, we can say that for the case of physical properties, we just or the mechanical properties, we can say that any mechanical property so by saying mechanical property, I can say that the fundamental mechanical properties are the elastic constants of a material. So I can say that the elastic constants. So any mechanical property, albeit elastic constants, that varies with axial strain and axial stress, so it's not just only varies, I mean, we can also say that it depends on. So any mechanical property that or the elastic constant that depends on axial strain and axial stress are anisotropic, or we can say are likely to be anisotropic. Are likely to be anisotropic. Okay, now having this definition, we come to what we know as monoclinic crystal system. So studying structural geology essentially to know about microstructures and deformation mechanisms, essentially the crystalloplastic deformation mechanisms, we ought to have a good grasp on the basics of crystallography and mineralogy. because we mostly study the thin sections of rocks, and from their physical and optical properties we try to determine the deformation that would have taken place in the rock. So for that we should know about the basics of crystallography and mineralogy, and for that we also need to know about the different classes of crystals and the crystal system. So monoclinic is, as we know, is the least amount of symmetry is present there, least amount of symmetry. That means it is highly anisotropic. So what are the, I mean, how to identify a monoclinic system is that we know A is not equal to B, and it is also definitely not equal to C. These are the unit lengths of lattice, right? So these are the unit cell parameters. And with A, B, and C, if this is A, this is B, and this is C, we have different angles. So the angle between A and B axis is gamma, angle between C and B axis is alpha, and angle between A and C axis is beta. Okay? So these are the different angular relations between the unit lengths of the crystal. So for monoclinic system, alpha equals to gamma is equal to 90 degree. So these two angles are 90 degree, of course, but beta is not equal to 90 degree. So we have neither symmetry in the length of the unit cell dimensions, and nor do we have any common angles that can be symmetric. So that's why monoclinic systems have very less symmetry present in their crystal structure, and that means it is highly anisotropic. So now, talking about the different options, if I say bulk modulus, that is denoted by K, what is bulk modulus? Bulk modulus is the volumetric deformation, right? So if I have an initial volume V0 and the final volume is Vf, then the change in volume with respect to its initial volume is the bulk modulus. That's how we define it. So bulk modulus essentially talks about the volumetric deformation. So whenever we are talking about volumetric deformation, we are talking about the bulk of the material without considering its direction, right? So of course, bulk modulus is not anisotropic is there in this case, right? And then if I say about compressibility, the compressibility C, it is nothing but the reciprocal of the bulk modulus. So that means this is also not anisotropic, right? And if, do you think that is there any meaning for the term density modulus? Of course not, because density modulus is ultimately density, and density is also the function of volume, not direction. Function of volume, right? So definitely this is also not anisotropic. So what remains is the Young's modulus, right? So why the answer is Young's modulus even? Because Young's modulus E, this is by definition is the axial stress by axial strain, right? So that is why this is definitely anisotropic because it depends on uh, the axial strain specifically. So the answer is Young's modulus, of course. But can you say another physical or mechanical parameter? I mean, other than the Young's modulus, the first thing that comes to your mind, which will be very much anisotropic, even more anisotropic than the elastic modulus or the Young's modulus. Can you okay, say any of the elastic constants that comes in your mind? Sorry, Pawan, I can't hear you.
Uh, I think it's to change it direction. More anisotropic will be this color is there.
Sorry, if you're talking about color.
Yeah, yeah, color.
No, yes, definitely color will be different, but I am talking about any other elastic constants or mechanical properties. So color is a physical property, of course, but it's not mechanical. So can you name any other mechanical constants like elastic modulus? We have learned another constant, which is even more anisotropic in nature for this kind of materials.
Not able to recall, sir. Abhi. Kindly tell.
Okay, yeah. So the answer is Poisson's ratio, right? So Poisson's ratio is another because Poisson's ratio by definition is the lateral strain divided by longitudinal strain. So it is essentially is a function of direction, even more
Okay,
so
okay.
than the even more so than the Young's modulus. So Poisson's ratio is another such mechanical parameter that is uh, that is anisotropic. I mean, they are likely to be anisotropic. So another is the rigidity modulus or the shear modulus. It's also anisotropic. So anything other than the bulk modulus can be anisotropic. Okay. So it was the first question. So let us move on to the second question, which is under compressive stress, a rock displays a strain hardening exponent of 0.3. If the stress coefficient of the stress strain relation is at 75 megapascals, how much strain is required to deform the rock to a stress of 50 megapascals? So this is something new. I hope that it wasn't in the lecture. I mean, not yet. You should learn about it in the upcoming lectures on deformation mechanisms. But I can say that we have already learned about the topic, which is the strain hardening thing. Okay, so what is strain hardening? So the concept of strain hardening is that if I have a stress strain curve like this is my stress, this is my strain. So up to the yield point, so this is my yield stress, sigma y, this is my yield stress. So yield stress by definition it is the maximum limit of elasticity. So beyond the yield stress, a material should either rupture that means it will follow the brittle deformation path, that means there will be a loss of cohesion, or it will continue to deform so in the plastic deformation domain, where the cohesion will not be lost within the material. I mean, it will essentially be a ductile material, but there will be a permanent change in the size and shape of the rock. That means the deformation will be plastic. So below the yield stress or the yield strength of the material, all the different deformation are theoretically elastic. But if we go beyond the yield stress, the material will behave as a plastic material. So for a plastic material, there can be three cases. The stress strain curve can either go like this, or it can go like this, or it can go like this. Right? So this path, this is called the strain hardening path. This path is called ideally plastic path. And this path is called as strain softening. Right? So why is it called strain hardening? Because say if I am at a strain level of sigma 1 and I want to deform the material to a strain level of say sigma 2, sorry, epsilon 2. So I was initially at epsilon 1, and then and now I am trying to deform my sample to a shear strain, or not, I mean, a strain to epsilon 2. But for to do so, I need to have to apply a load or stress. If this was sigma 1, then it is sigma 2. By definition, sigma 2 will be greater than sigma 1, and that is the concept of strain hardening. Hardening means the material is becoming more and more hard to deform as we go on. Right? That means we need to have to apply more amount of stress to get to the desired amount of strain that we want. But if for the same for ideally plastic material, we see that from going from epsilon 1 to epsilon 2, sigma 2 minus sigma 1 is 0. Right? So for strain hardening material, strain hardening material, going from epsilon 1 to epsilon 2, that means we are taking the stress from sigma 1 to sigma 2. That would mean that sigma 2 minus sigma 1 should be greater than 0. For strain hardening materials, we see a relation, that is stress is equal to stress coefficient K times epsilon to the power n. This is a strain hardening power law relation between stress and strain. Right. So now we have to go to our problem that is saying that under compressive stress, a rock displays a strain hardening exponent of 0.3. So we have given the value n is equal to 0.3, right? If the stress coefficient of the stress strain relation is at 75 MPa, that means K has been given as 75 MPa. How much strain is required to deform the rock to a stress of 50 megapascal? We are asking the value of, we have been given the value sigma of 50 MPa, and we have to determine the value of epsilon. Right? So to do so, we should take log on both sides of the equation, and from that we get log sigma is equal to log k plus n log epsilon. Now log of 50 is equal to log of 75 plus 0.3 log epsilon. Okay? Or log of epsilon is equal to, so what will be the logarithm value of 50? We have to calculate it. So keep in mind that I am talking about log base 10. Okay, so you can say log of base 10. So log 50 is 1.69
0.69.
MPa.
1.69.
1.69. Okay. So 1.69, and then for log 75 we have
1.87.
1.87, right? Log 75. Here, 1.87 divided by 0.3. So that means we have 69 minus 1.87
That will
minus
be
zero point
minus
0.1.
minus 5.
Yeah, minus 0.18 divided by 0.3. Minus 0.6. So that means epsilon will be 10 to the power minus 6, right? 10 to the power minus 0.6. 10 to the power minus 0.6. Yeah, so the value is 0.25. So epsilon is 0.25. That means 25% strain, right? So this is the answer. So from, deforming the material with a strain hardening exponent of 0.3, if I want to deform the rock to a stress of 50 MPa, then I need to apply 25% strain from its initial shape and size as well. So this is how strain softening relations are being established as well. But in that case, the value, as you can know that in case of strain hardening, the value of n is positive. And if I have strain softening, then of course the value of n will be negative. And that's how we identify whether the relation between stress and strain is strain hardening or strain softening. So strain hardening and this exponent, this strain hardening and strain softening exponent, this has a range of 0 to 1. So the range should theoretically lie inside this, and for ideal cases, n ranges mostly within 0.1 to 0.6, not more than that. That's the ideal range for rocks and other metals and composites to show this kind of strain hardening experiment. Okay, so moving on to the next question, question number 3. It says that a rock having density of 2.7 gram per cc and bulk modulus of 4.5 into 10 to the power 10 Newton per meter square is subjected to compressive stress that produces a shear wave upon fracturing. The shear wave travels through the rock mass with a velocity of 3,800 meter per second. Find the Young's modulus of the said rock. So in this case, we have to relate a formula 1 or 2 to get the value. I remember that in the previous discussion session as well, I saw we solved this kind of problem, but it was, I mean, this one is more elaborate than that. So just let us see what information we have been given. So we have seen that we have been given with density rho. It has been given 2.7 gram per cc. Now keep in mind that in any kind of competitive examinations, it is often seen, has been often seen that the problem that has been given is very simple, but the trick is to get the formula with uniform units and dimensions. So just you can see that this formula has been given in CGS unit, the density, that is 2.7 gram per cc, but the rest of the formula is given in SI. So, and the thing is that doing problems or solving problems with SI unit is much more easier than to remember the conversions between the CGS and SI units. So let's just convert the initial data into SI unit. So 2.7 gram per cc means we have 2700 kg per meter cube. That is the density in SI. Okay. So the density has been given. We also have been given with the bulk modulus of the rock, which is K, of course, is 4.5 into 10 to the power 10 Newton per meter square. That means 4.5 into 10 to the power 10 Pascal, right? And we have been given with the velocity of the shear wave, or Vs, that is 3,800 meter per second. So we know that Vs has a formula of mu by rho, where mu is the rigidity modulus or shear modulus of the material. Right. So we can determine the value of mu just as Vs square times rho. So that would be 3,800 square times 2700. That means you can calculate it me as well. 3800 square times 2700. So that is 38.9 into 10 to the power 9. It also has a unit of Pascal, right? So this is the value. Now we can use another formula for Vp, velocity of the P waves. Vp has been is written as square root of bulk modulus plus 4/3 of rigidity modulus divided by density. So Vp, you can calculate it as the bulk modulus is 4.5 into 10 to the power 10 times, sorry, not times, plus plus 4/3, that means 1.3 into 38 to 10 to the power 9, right? Divided by rho, which is 2700. So 1.3 times 38 times 10 to the power 9. So that's 4.5 in 10 to the power 10 plus 49 into 10 to the power 10 by 2700. So that means we have 49 plus 4.5, 53.5 into 10 to the power 10 and whole divided by 2700. And if we square root to that, we get 44,514. This is the velocity we are getting meter per second. This is the velocity of P wave. Right? So we have the velocity of P wave, we have the velocity of Vp, sorry, Vs. We also have the bulk modulus, sorry, not bulk modulus, we also we have the density. So based on these things, we can calculate the dynamic Young's modulus of the material with the given formula, which is rho times V S square multiplied by 3 Vp square minus 4 Vs square divided by Vp square minus Vs square. So by putting these values, you can calculate the uh, Young's modulus of the rock. We can surely do that. So that would mean 3 into 44,514 square minus 4 into 3800 square. This whole number, it is then divided by 44,514 square minus 3800 square. So we are getting the value of 2.99. So this is 2.99, and we have the density of 2700 into, we can say, multiplied by the velocity of the S wave, which is 3800 square multiplied by 2.99. So we can compute this value as 2700 times 3800 square times 2.99. So the answer is 116.5 GPa. So this is the elastic modulus of the material. Okay. So you can use this formula, rho Vs square multiplied by 3 into Vp square minus 4 Vs square. Another thing is that if you subtract, so we can see from the formula of the velocity of P wave, it is root over of k plus 4/3 into mu divided by rho. So surely if you just see Vp square as a formula, you can write k by rho plus 4/3 mu by rho, right? Now mu by rho is nothing but Vs square. Right? So we can also write Vp square is equal to k by rho plus 4/3 Vs square. So from that we can see 3 Vp square minus 4 Vs square is equal to 3k by rho. So instead of calculating this entire value numerically, we could just plug in this formula, that 3 Vp square minus 4 Vs square will be 3 times bulk modulus divided by rho. Okay. So this was the third question. Now getting to the fourth question. In a layered rock, if the viscosity of layer A is eta A is larger than the layer B's viscosity, which is eta B, then upon compression, which of the following structure will form? Option A is, if layer A is surrounded by layer B, then layer A will form Boudinot structure. Option B is, if layer B is surrounded by layer A, then layer B will form folded structure. Option C is, if layer A is surrounded by layer B, then layer A will form folded structure. Sorry, it should be layer B surrounded by layer A. No, it is right. I guess, sorry, I just thought it's repeated. Okay, so if layer A is surrounded by layer B, then layer A will form folded structure, and finally option D is if layer B is surrounded by layer A, then layer B will form pinch and swell structure. So what the question is saying that we have two different layers. One is the matrix rock we can consider, and another is the so if this is high viscosity and this is low viscosity, then upon application of compression, we would see this kind of structure. And if the opposite is the case, that a high viscous layer is sandwiched between two low viscosity layers like this. So this is high viscous and this is low viscous. Then upon compression, we would see that the layer has been folded like this. Right? So high viscosity layer will always fold. Okay. So what is given is that in a layered rock, viscosity of layer A is larger than viscosity of layer B. That means eta A is greater than eta B. So if this is layer A and if this is B, it is most likely that if A is surrounded by layer B, then it will be folded because high competent layers are always folded. So given that, we see that option C fits to the answer, which is if layer A is surrounded by layer B, then layer A will form folded structure. And that is true because layer A has higher viscosity than layer B. Okay. So this was the question about the competency contrast. Okay, so moving on to the next question. A rock has a tensile strength of 3.5 megapascals. If the angle of internal friction of the rock is 35 degrees, find the amount of resolved shear stress if the normal stress is 65 megapascal. So our job is to find that what will be the shear stress acting on a plane of particular orientation on the rock, given that the normal stress is 65 megapascals and the tensile stress is 3.5 megapascals. So, uh, So let us talk about Coulomb's fracture criteria. So according to Coulomb's fracture criteria, so if I plot the shear stress and the normal stress along y-axis and x-axis respectively, then the Mohr circle that we know, what is a Mohr circle? Mohr circle defines the state of the differential stress acting on a particular plane subjected to stress or external load. So the midpoint of this circle, Mohr circle, is the effective mean stress. This point is sigma 3. This point is sigma 1, of course. And the maximum value for this envelope will be sigma s, which is the shear stress that acts on the plane, given that the plane has an orientation of 2 theta with respect to sigma 1. So that is the concept of the normal Mohr circle diagrams. Now, if Coulomb has said that an envelope or a tangent can be drawn by subsequently plotting the different range of differential stresses as Mohr circles, and then if we just join the tangent to them, we will get such straight line with the following equation: sigma s is equal to some constant plus some slope times sigma n. So this is the equation of Mohr envelope. Now this is this is known as the cohesive strength of the material. Coulomb has particularly made an assumption that C, that is the cohesion of the rocks, can become equal to twice of the tensile strength of the rock. So T is the tensile strength of the rock. And of course, we have this slope, and this slope is defined by mu, which is in this case the internal friction that controls the fracturing within the rock. Mu is the internal friction, which is described as tan phi. So this phi is the angle of internal friction. So this is so the formula ultimately becomes sigma s is equal to 2t plus tan of phi times sigma n. Right? So we have been given that the tensile strength of the rock is 3.5 megapascals plus tan 35 degree times 65 MPa. So, so this is 7, right? Plus point tan 35 degree is 0.7 times 65. So we ultimately get a value of 52.5 megapascals. So the value of shear stress is 52.5 megapascals. So this is in brief. We could talk about the Coulomb's fracture criteria that tells us that we can consider uh, the cohesive strength of the rock as the twice of the tensile strength of the rock if it is given. Okay, so let us move on to our next question. So the sixth question says that an oceanic plate has an effective elastic modulus of 90 into 10 to the power 7 Newton per meter square, Poisson's ratio of 2.7, and average thickness of 5.5 kilometers. During subduction, calculate the bending stress per unit volume experienced by the plate. So this is a bit new concept for those who have taken this course. Generally, it is not yet been taught. So a plate is by definition is a rigid object, rigid body. But when we try to see the or to model the process of subduction, we see that if this is the thickness of the plate, we see that the plates are being bent at the trench. So this is how the plates are being bent, and they continue to subduct. Right? So, of course, if the plate is much thicker, the curvature of bending would also become very high. So we can say that bending a plate requires a bending moment. Bending moment means we need to apply a particular amount of force from some arbitrary distance of the plate or a rod or a one-dimensional object to bend it. Right? So we need a bending moment for that. The work done, so bending moment is basically the work done to bend a certain distance, a certain length, whatever. And this is a function of the thickness, the elastic modulus, and Poisson's ratio. So all these three things are associated to each other, and only if we have the value of this elastic modulus, thickness, and Poisson's ratio, we can compute the bending moment of a plate. And the bending moment of a plate requires a certain stiffness calculation, that how much stiff a plate is, based on which we can say that how much moment we need to, uh, how much moment we require to bend the plate. So the stiffness of the plate, the bending stiffness, or commonly known as the flexural rigidity, which is expressed as D, is given by a formula of elastic modulus of the Young's modulus divided by 12 into 1 minus nu square times h cube, and this thing has a unit of Newton meter. So this is the formula that we should consider for calculating the textural rigidity of a plate. Now we have been given that the elastic modulus has a value of 90 into 10 to the power 7. Poisson's ratio has been given a formula of 0.27, and thickness of the plate H is 5.5 kilometers, and it means 5500 meter. Right? So if you just plug in these values, you can say that D can be calculated as 90 times 10 to the power 7 times 5.5 into 10 to the power cube divided by 12 into 1 minus 0.0729, right? 27 square. So ultimately we can get the value of 41.25 times 10 to the power 10 GPa. No, sorry, just Pascal, not GPa. 41.25 times 10 to the power 10 pascals. That means 412.5 gigapascals. Now, a plate is a two-dimensional object, right? So it not only has a thickness, but it is two-dimensional. I mean, three-dimensional object. So it not only has a thickness, but it also has an area. So if we divide B by the volume of the rock, this will become the bending stress per unit volume. The bending stress per unit volume means this will be one cube, of course. So sigma B will be around 412.5 GPa as well, right? Because D has an unit of Newton meter, and if I just divide it by D H cube, we will get Newton per meter squared. It's a unit of stress. So bending stress per unit volume, that would essentially mean D by H cube. So we can calculate the bending stress per unit volume from that. So this is how we can assess how much stress or is required to bend a plate for a given radius of curvature. And also the thing is that uh, the radius of curvature of a plate the bending radius of curvature of a plate would increase if we increase the thickness of the plate, and that is an important information for assessing the deep of the subducting plate, the subduction zone. Okay, moving to the next question. So the question says that if the density of quartz is 2650 kg per meter cube and the density of orthoclase is 2550 kg per meter cube, the lithostatic pressure due to granite with 68 modal percentage of quartz and 32 modal percentage of orthoclase at a depth of 10 kilometers will be this much amount of kilowatt. Okay. So modal percentage means this is the volume percentage we're talking about, right? So we need to calculate the bulk density of granite, and that would be modal percentage of quartz times density of quartz plus modal percentage of orthoclase times the density of orthoclase. Okay. So raw granite, that would be 0.68 times 2650 plus 0.32 times 2550. That means the density will be 2618 kg per meter cube. So this is the bulk density of the granite we're talking about. So now, as we have the density, we can easily calculate the lithostatic pressure. So the formula for lithostatic pressure will be E is equal to rho GH, right? So the rho is 2618 times 9.8, and the given depth is 10 kilometers. So 10,000 meters, right? So if you just calculate it, we get 2618 times 9.8 times 1000, sorry, 10,000. So it is around 256 2565.64, this much amount of bar. That means it will be 2.56 kilowatt. Okay. For using an information, you can write that 1 bar is equal to 0.1 megapascal. So 1 kilowatt means 100 megapascal. So this information is used to convert from the unit of megapascal to bar. Okay, so this was the 7th question. We have some 8 questions left for today's discussion session. So just quickly go through them. Okay. The 8th question says that due to an event of deglaciation, a bent crustal depression is returning to its initial position through viscoelastic rebound and isostatic adjustments. Right? So if the thickness of the crustal plate is given as 40 kilometers and the average density and viscosity of the underlying mantle is 2.99 gram per cc and 2.8 times 10 to the power 22 Pascal seconds respectively, calculate the relaxation time of the underlying mantle given the wavelength of the crustal depression is thousands kilometers. So this information is needed to calculate the relaxation time of the mantle. So what happens is that, say for example, there is a glacier. So this is crustal plate, and we are assuming that beneath this lies the mantle. Okay. Now we had a glacier here, glacial mass, and that caused these crustal plate to bend like this. Right? So this bending is also associated with the stiffness or the flexural rigidity that we initially talked about. But to accommodate this deformation of the crustal plate, the mantle has to flow from this position to away from this, right? Otherwise, this deformation would not have been accommodated inside the earth. And now, due to deglaciation, all the ice is removed. So the crust is actually showing a viscoelastic rebound. That means due to its viscoelasticity, the crust is trying to go back to its original shape. And as it is trying so, the mantle is also trying to flow in the reverse direction, actually to push the crust from below. And along with the crust, the mantle is also showing viscoelastic deformation. Viscoelastic deformations. Right? So among such is this relaxation time that can predict how much time is required for this flow of the mantle to come in equilibrium, and that would mean that the isostatic adjustments are over. Only then the mantle could come in equilibrium, right? So in a way, if we could calculate the relaxation time, then we could predict how much time it would take to completely come back to the initial equilibrium, initial isostatic equilibrium after deglaciation. So all these things, this has a very straightforward formula, analytical solution is that if this is the relaxation time, tau, this is the mantle relaxation time, tau is equal to 4 pi eta divided by rho m times g times lambda. Eta is the viscosity, and we have the value of 2.8 times 10 to the power 22. Rho m is the density of mantle, average density of mantle, which has a value of it's been given as 2990, sorry, kg per meter cube, and lambda is the wavelength of the crustal depression. Right. So if you just plug in these formulas, we can calculate tau s 4 into 3.14 times the viscosity is 2.8 into 10 to the power 22 pascal seconds divided by 2990 times 9.8 times 1000 into 10 to the power 3 converting into meter. So that means we effectively get, by calculating these values, 4 into 3.14 times 2.8 times 10 to the power 22 divided by 2990 times 9.8 times 10 to the power 6. So you get 1.2 into 10 to the power 13 seconds. So if you just convert it into years, we will get 3.8 billion years. So the relaxation period of the mantle will be 3.8 billion years. So this is the idea of viscous relaxation of mantle and how it can be associated with crustal deformation. And this is a prime example of viscoelastic geological models that we have already learned in the week 5 contents. Okay, moving on to the next question, question number 9. The seismic slip rate, seismic slip of a fault after earthquake is measured to be 0.5 meter, and the fault area is estimated to be 250 kilometers square. So if the seismic moment during the rupture was 3.75 times 10 to the power 18 Newton meter, then calculate the rigidity modulus of the rock. Also, if the density of the rock is 2.78 grams per cc, calculate the shear wave velocity that traveled through the rock during the rupture. So we have been given an information which is the seismic moment of the rock. Which is 3.75 times 10 to the power 18 Newton meters, right? And also given is the density. No, sorry. Apart from density, we have been given is that the rupture length of the fault and the contact area. So that means, so if I have a fault plane, so if this is the new area produced because of the rupture, so if this is the dimension D and area A, this is the new surface area produced by the rupture, produced because of the rupture, sorry. So if you just calculate the moment based on this area, we can get the seismic moment as the rigidity modulus times A, area, times T, slip length. Together we can get this formula for seismic moment. So seismic moment is essentially is a function of the rigidity modulus of the rock type. So given that all these value, we can calculate mu as the seismic moment divided by A times D. It has been given 3.75 into 10 to the power 18. The area is 250 times 10 to the power 6 times 0.5. So we get the value of 30 into 10 to the power 9 pascals, right? That means 30 GPa. So this is the rigidity modulus. Also given is the density of the rock, which is 2780 gram per cc. So if we just plug in the value Vs with the formula 30 into 10 to the power 9 divided by 2780 and take the square root, we get 3285 meter per second. So this is the velocity of the shear wave, and this is the rigidity modulus. Okay, so this is how we can apply the seismic moment formula. We can also even calculate the seismic moment magnitude based on the how much energy is released. So seismic moment is basically how much energy is released to produce the fracture. That is how we calculate. That is how we conceive the concept of seismic moment. And seismic moment can also be used to calculate the rigidity modulus, the moment magnitude, and from that we can also even find the velocity at which the energy has been dissipated from the fracture, which is the Vs. Okay, so this is how we have been calculating the rigidity modulus from the seismic moment. Okay, so moving on to the next question. Question number 10 says that a linearly viscous fluid requires 80 MPa shear stress to flow at a strain rate of 2 into 10 to the power minus 14 per second. Another elastic material, which is at room temperature, requires 40 megapascal to reach up to the yield point at an axial strain of 10%. Now, if these two materials are combined as a Maxwell material, find the strain rate of the system deformed at a normal stress of 100 megapascal with a rate of 1 kilonewton per hour. So as we know that Maxwell model contains the linear viscous component plus the elastic component, right? Now first, for the viscous component, we see that the shear stress tau is 80 MPa and the shear strain rate has been given as 2 into 10 to the power minus 14 second inverse. So we know that tau is equal to 2 eta times shear strain rate. Therefore, eta is equal to tau by 2 gamma dot. That means we can calculate it as 80 into 10 to the power 6 divided by 2 into 10 to the power, sorry, this will be 4 into 10 to the power minus 14 second inverse. From that, we can arrive to a value of 2 into 10 to the power 21 Pascal second. So this is the viscosity of the material. For the elastic material, we know the relation sigma is equal to E times epsilon, right? So E is sigma by epsilon, sigma by E, right? Now the sigma is given is that the yield point, which is 40 megapascals, means 14 10 to the power minus, 14 10 to the power 6, right? And the strain is 10%, that means 0.1. So ultimately, the elastic modulus or the Young's modulus of the material will be 4 into 10 to the power 8 pascals. Okay? Now, for Maxwell viscoelastic material, the strain rate is given as 1 by Young's modulus times, sorry, 1 by Young's modulus times d sigma dt. This is the stress rate plus sigma by eta. Now the stress rate is given as d sigma dt as 1 kilonewton per hour. That means 1000 Newton per 3600 second. So which is equivalent to 0.278 Newton per second. And the value sigma itself is 100 MPa. That means 100 into 10 to the power 6 Pascal. So if I just plug in the values, we get strain rate is equal to 1 by 4 into 10 to the power 8 times 0.278 plus the stress is 100 megapascal, means 100 into 10 to the power 6 divided by eta is 2 into 10 to the power 21. So doing all the calculations, we can arrive to a value of 7 into 10 to the power, roughly approximately the value of 7 into 10 to the power minus 11 per second. So this will be the effective strain rate at which the material will be deforming when they are combined into a Maxwell type linear viscoelastic material. Okay, so move on to our next question, question number 11. Upon increasing the shear rate, a material that shows non-linear increase and decrease in apparent viscosity are called option A, viscoelastic and thixotropic respectively, option B, rheotropic and thixotropic respectively, option C, Bingham and viscoelastic respectively, and option D is Bingham and rheotropic respectively. So for this, we just need to know some information. So rheotropic material Rheotropic material. So these are a material which shows nonlinear increase in apparent viscosity with time, for which a constant constantly increasing shear rate. Okay, so this is called a rheotropic material, and thixotropic material is just opposite to rheotropic materials. So for the definition of thixotropic materials, it will be a material which shows nonlinear decrease in apparent viscosity with time, for which a constantly decreasing shear rate is applied. For which a constantly increasing shear rate is applied. So in this case, option B will be the correct answer. That means with increasing, if the non-linear increase in viscosity is observed, then it is of course rheotropic material, and if non-linear decrease in viscosity is observed, then of course the material will be thixotropic in nature. Okay. So question number 12 says that a density log for a region gave the density of the formation fluid and the rock matrix to be 950 kg per meter cube and 2540 kg per meter cube respectively. Also given the bulk density of 1950 kg per meter cube. If the pore pressure is related to the porosity in the form of sigma p is equal to 6.85, it will be plus, I guess. So if the porosity is related in the form of sigma p plus sigma p is equal to 6.56 plus 8.5 times phi square, where phi is the porosity, then calculate the effective mean stress of the porous rock at a depth of 5 kilometers. So what the information we have been given is that the pore pressure is given as sigma p is the pore pressure, it is 6.56 plus 8.5 times phi square. Phi is the porosity. So we have to calculate the effective mean stress at a depth of 5 kilometers for this porous rock. So for that, we need to estimate the porosity of the rock at first. So what information has been given is that we have the bulk I mean density of the formation fluid, which is, you can say, rho f. We have been also given with the density of the matrix, which is rho m, and the bulk density, which is rho bulk. So these three parameters are related together with the formula as rho b is equal to phi times rho f plus 1 minus phi times rho m. So if you just know the density of the fluid, density of the matrix, and the bulk density, you can easily estimate the porosity. So phi is the porosity. So what we have been given with is the values. Density of the fluid is 950 kg per meter cube. Density of the matrix is 2540 kg per meter cube. And the bulk density is, of course, 1950 kg per meter cube. So if you just plug in the values, you can write 1950 is equal to, sorry, is equal to 5 times 950 plus 1 minus 5 times 2540. So this is 955 plus 2540 minus 25405, or from that we can estimate phi as 1950 minus 2540 divided by 950 minus 2540, 0.37. That means 37% porosity. So we have got the value of phi, and then we can put the value in the given formula. Sigma p is equal to 6.56 plus 8.5 times 0.37 square. 6.56 plus 8.5 times 37 square. 7.72. So 7.72 megapascal is the value of the pore pressure. Now, the density of the bulk rock is 1950 kg per meter cube. So we can use this density will be used to calculate the lithostatic pressure. So the lithostatic pressure sigma 0, that is rho GH, rho B GH, right? So rho B is 1950 times 9.8 times a depth of 5 kilometers in 5,000. So 1950 times 9.8 times 5,000. So it is around 95 megapascal, right? Then if we just calculate the effective mean stress, that is nothing but sigma 0 minus sigma p. That means 95 minus 7.72, right? So it is around 87.3 megapascal. So this is how you can relate the pore pressure with porosity, and the porosity, I mean, this is how we can relate the density with porosity, and porosity can be used to estimate the pore pressure, and eventually the pore pressure can be used to calculate the effective mean stress at a given depth inside the earth. Okay, so moving on to the next question. The deformation of a material is said to be Newtonian when strain is really linearly proportional to stress. Option B, the rate of strain is linearly proportional to stress. Option C, strain is not proportional to stress. And option D is strain is independent of stress. So which of the option will be correct?
It's option B is
Exactly, option B, because that is the definition of viscosity, right? So we plot the stress or shear stress or normal stress, whatever, and we plot the strain rate. So rate of strain versus this plot is a straight line, and the slope is the viscosity. So this is the, when this is a straight line, this is a Newtonian fluid. Newtonian fluid, or ideally viscous material, right? So that is why option B is correct. Okay. Which of the following properties of a rock with fluid filled cracks would best represent its rheology? Option A, elasticity. Option B, plasticity. Option C, viscoelasticity. And option D, linearly viscous. So for example, if you have a rock and this is a crack, and you have fluid in it. Right? So the fluid will be obviously viscous, right? And the rock, considering a shorter window of deformation, so the rock, considering a shorter window of deformation, will be or will behave as elastic. That is why elastic waves, that means the seismic waves, can pass through rocks, right? Because in shorter duration, every rock can behave as elastic material. So of course we have viscous fluid and an elastic rock. So together, if we just try to deform, so the deformation will be viscoelastic in nature. Okay.
Sir, that's right.
Yes.
That will be viscous, but that the temperature of the fluid will also govern some. If it's hydrothermal temperature, different temperature is there, then the
Yeah,
nature
but
will be different.
temperature, of course, but the temperature, the way the temperature will be dissipated into the rock, that will matter. So in case of temperature, in case of high temperature fluid, the dissipation of heat, the dissipation time of heat into the rock and its composition, essentially the melting point, will control the rheology. Not
Okay,
as
thank you.
per control, it will affect the rheology.
Effect. Yes.
Yes, it will affect the rheology. Okay, so moving on to the last question for today's discussion. The yield strength of a rock at Earth's surface is 50 megapascal. The rock shows a stress temperature pressure relation as follows. Sigma is equal to 1.5 sigma 0 minus 1.7 times 10 to the power 6 divided by del T square plus 3.1 times del T cube. For a normal geothermal and geobaric gradient inside Earth, find out the strength of the rock at 3 kilobar pressure. Consider pressure at kilobar and temperature in degree centigrade in the empirical equation. So we have been given with an empirical equation which is in the form of the empirical stress temperature pressure relation sigma is equal to 1.5 sigma 0. So this is the initial yield strength of the rock. Minus 1.76, 1.7 into 10 to the power 6 divided by del T square plus 3.1 del T cube. Okay. Now it has been told that consider normal geothermal and geobaric gradient. So what is the normal geothermal gradient?
What 1 degree per 30 meters?
No, it's so the normal geothermal gradient, which is dTdh, that is 25 degrees centigrade per kilometer, and
Sorry.
normal geobaric, that means pressure gradient, which is dTdh, which is 0.3 kilobar per kilometer. Okay, so depth at 3 kilobar pressure will be simply multiplying this depth pressure gradient times, dividing the total pressure divided by this 0.3 gradient, it will give us the depth of 10 kilometer, right? So we know that at 3 kilobar pressure, the depth is 10 kilometers. Now, if we just use the temperature del T it will be 25, this is the gradient, times 10 kilometer minus surface temperature, which is 25 degrees centigrade. That means we get 225 degrees centigrade. Right? So this is the temperature at 10 kilometers of depth. And this is the pressure at 10 kilometers of depth, because the pressure at Earth's surface is really negligible compared to the pressure at 3 kilowatt. So that's why we can just consider del P is equal to, consider del P is equal to 3 kilowatt and del T is equal to 225 degrees centigrade. So if we just plug in the values, we get 1.5 times 50 minus 1.7 in 10 to the power 6 divided by 225 square plus 3.1 times 3 cube. So we get 75 minus 1.7 times 10 to the power 6 divided by 225 square
50,600.
plus 3.1 times 9. So that's it. Yes, 69.32 megapascal, right? So we know that by increasing pressure, we increase the yield strength, and also by increasing the temperature, we decrease the yield strength. But at least below 300 degrees centigrade, the effect of pressure inside Earth is much more than the effect of temperature. So that is why the increase in temperature does not even affect that much when you're talking about crustal level, unless and until there are some hydrothermal event or some intrusion of dike or magmatic events. But other than that, the main effect of temperature sets into play whenever we're talking about the brittle ductile transition and wherever we are going from the crust to the mantle. Right? So that crust mantle boundary, and even in the upper mantle or in the lithospheric plate, these kind of situations where the temperature would actually play a role, but until and unless the temperature is higher than 300 degrees centigrade, the pressure dominates over the rheological behavior of the material. Okay, so that is how. So this was a simple example of such kind of empirical relation between pressure, temperature, and stress. So with that, I complete today's discussion session. And for the upcoming week, we have, in week 6, we have the deformation mechanisms of materials. Mostly we will cover the crystal plastic deformation mechanisms such as dislocation, diffusion, and we will know different modes of deformation such as subgrain formation, subgrain rotation, grain boundary migration, bulging, recrystallization, and then we will go to dynamic, from static crystallization to dynamic recrystallization to static recrystallization, and then we will finally talk about diffusive mass transfer. So in the upcoming live session, we will mostly follow numerical problems related to different deformation mechanisms, estimating strain rate from deformation mechanism maps, and we will also learn some new techniques that are applied in the research field of structural geology. So with that, I end today's discussion session. Thank you for joining.
Thank you, sir.
Thank you.